Hello and welcome to our talk on DP4DS, which stands for Data Provenance for Data Science. Real title is up there on the slide. This is joint work with Adrian Chapman at Southampton, Giulio Simonelli, who is a former master student of Professor Riccardo Torlone at University di Roma III in Italy, and myself, Paolo Missier at Newcastle. So what's the motivation here? We're all familiar with this picture where you have basically a model that you learn from a training set that is the result of a pre-processing phase that starts with the selection of data sources, acquisition, wrangling, and then a number of operators which massage the data in a way that is then suitable for input into a model learning algorithm. So we all know there are problems with the resulting models, maybe bias, fairness issues, performance issues, strange predictions that we can't understand. And it all goes in the big chapter of explainability of machine learning. Our focus in the explainability area is on the pre-processing side. And we make the hypothesis that if we can collect enough provenance, basically trace everything at a very fine granularity that happens in the pre-processing phase, then we stand a chance to actually explain some of the decisions that, or record rather, some of the decisions that are made at this point, and then use those to provide explanations regarding what happened in the model. We do this by collecting provenance. So this is kind of a graph that looks backwards, where entities and activities, map from various elements of the entire processing pipeline. If you are familiar with the metadata model for provenance, this is what we use here. The question is, how much provenance can we collect and should we collect? And then some of this is constrained by the nature of the program. So for example, if I have a completely opaque program PO, then there's not much I can say. Basically, every output depends on every input. Not probably very useful. If I manage to open up the program and make it transparent, then I can observe it in the execution, and perhaps I can say that, for example, Y2 depends on both inputs through F, while Y1 only depends on X1. If I go one step further, then I not only have a transparent program, but also have a transparent set of data. And for example, data frames, or tables, if you prefer, and I may end up with provenance statements that are more granular. A particular data cell in one particular output is derived from only a selected few inputs. And then if you then extend this idea to a whole pipeline of transparent programs, then you end up with a very granular provenance graph where every single element in the output has its own provenance all the way to the inputs. Okay, so this is where we sit. We kind of obsessively try to collect provenance at the finest possible levels to see if it's practical, if it's efficient, and also if it's useful in practice. Okay, so what are these transparent programs? On the left, you have a catalog that is probably familiar to most of you. On the right, you have our own catalog that we put in the paper. And for each of these typical data science preprocessing operators, we provide a formalization. Okay, so roughly they fall into this data reduction, transformation, augmentation, big categories. But we now zoom in into one case. We take vertical augmentation here, of which one hot encoder is a classic example. Okay, so if you go from the general, okay, there's an operator that takes a data frame, changes either the value or the shape of the data frame through one operator, and then produces another one. So vertical augmentation is one such operator. Let's say new features Y are produced from the existing features X through the mediation on function F. As an example is I have zip code here, and I create new column age range, which is just a binning of people into age range depending on their actual age. Okay. So if we look at the provenance of the cells in age range, we find that we basically end up with small graphs, so as I call them, provelets that look like this. Okay, so there's E, which is the activity, which is the vertical augmentation operator, which has basically used the 24 and generated young, and in particular, young was derived from 24, and similarly, adult was derived from 28, and so forth. And because basically this is a very regular pattern, it's very tempting to use a template approach to create these little provenance documents. Okay, and this is what we do. So templates are available as part of the Prov ecosystem. So this is a valid Prov pattern, but actually values are replaced by variables in their own namespace. And then all we have to do is basically instruments the code so that every time an operator runs, you create these bindings between the variables that are mentioned in the pattern and the values as we progress through the data frame. And then you basically, by applying the bindings to the template, systematically you end up with all your little provenance fragments. Okay, you can do this across all operators. For each of the operators that we listed, we have a provenance pattern with the template, and then a method to acquire the bindings. How do we acquire actually the bindings? Well, the problem is making the code provenance aware, where it's really kind of arbitrary pandas Python code. And our approach is actually using a semi-transparent, semi-automated way, which uses a provenance tracker object, which encapsulates an underlying data frame. So as long as operations on the data frame are mediated by the provenance tracker object, this tracker here, then we are in business, because the tracker will observe and then generate the corresponding provenance for that use of the operator. And if you do this systematically, for example, instant generator, imputation, and so on and so forth, then we are in business. All of these operations become provenance aware. Okay, so I don't have time to go into further details on this, but basically, if each preprocessor is instrumented in this way, then at the end of an operator execution, we have a bunch of these provenance fragments. We encode them using JSON, which actually can encode Prov natively, and sticking it to a MongoDB database. Okay, and what happens next? This scales in the number of pre-processing operators, because they all kind of produce this provenance independently of one another, but they all comes together in a big provenance graph in Mongo. We then compress the provenance graph storage here, but we can also optimize on capture, basically remove or reduce overhead of capturing provenance by using Python multiprocessing, both when we write operators to disk and when we scan the data frame. Okay, and then we measure the corresponding time it takes to query the database. So Census is the largest data set in a set of 3 benchmark data sets. It's 30,000 records, with actually, if you look at the pipeline down here, it looks kind of innocent, but it touches it generates multiple versions of this data frame. We end up with about 4 million entities and nearly 10 million provenance relations. So this is sizable benchmark, and using this, we observe that, you know, for a data frame of over 1 million cells, we apply a number of compression techniques of a native MongoDB storage, and we have, you know, 70% improvement or 60% improvement in data frame scanning. Similarly, if you compress on the storage various tricks that I don't have time to go into, that in the details in the paper, we can compress quite significantly. And finally, for each of the 3 data sets, we have corresponding pipeline, and for each pipeline, we have a corresponding set of benchmark queries, which are documented in the paper. If we use the census pipeline queries, then we observe very promising query results, where most queries are essentially very inexpensive to run. So nearly out of time. This is a very short video. Hopefully the live talk will be a little longer. What we've done is experimented with the idea of collecting very fine grained provenance for data processing pipelines. And we demonstrated this is practical and efficient And one question is, how far can we this tracker approach go into capturing arbitrary or ever expanding set of operators? And more importantly, what is the killer app for such granular provenance? These are really the next step for us, challenging this approach on real world pipelines. This is all the time I have, and thank you all for your attention, and I will be available for questions. Thank you.